Hey, hi there. Congratulations. If you have come to this part, it means that you have completed your system Verilog session, and now you are coming to start off with the UVM. In this part of this session, we will introduce ourselves to UVM, and what you will see is that we have built the test benches using the system Verilog. So we have built our FIFO test bench, and when the basic promise of UVM is to make this process of building coverage driven constrained random verification much more easier and reusable, and having the ability to scale those test benches to much more complex designs. Okay, that is what is the promise of UVM, and we will look at how it is able to fulfill that promise as a part of this session. Okay, here is the agenda for the this session. So we will start off with our favorite question that will ask why, right? So why we need verification methodology? We'll quickly ask ourselves that question, and then we'll jump into what is UVM, and then we'll understand quickly a little bit of an how UVM has evolved, and the importance of understanding this evolution is that it will show you that because of evolution there is lot of redundancy, and also the size gets bloated, right? So that is the reason why we need to understand the evolution, and that helps us pick the right things to study and use eventually. And then UVM is nothing but a base class library, so we will understand like the core hierarchy of UVM, how it has been structured, and then we look at the like a very quick high, like a 10,000 feet view of the UVM test bench. And then we'll understand, I mean, I want to set some expectations, right? We will call out, or like yeah, we'll call out the elephant in the room. So we'll say, why is UVM so large? Let's ask ourselves that question, and then what is our strategy to conquer UVM? Okay, so we will discuss it, and after that, then next sessions will start going deeper to execute the strategy that we have thought out. So that is our overall plan of how we are going to accomplish the mastery or UVM. So why verification methodology? So one thing that's happening in the industry is that the overall designs are becoming very complex, and then different companies wants to focus on different problems. Okay, so every company doesn't want to solve all the problems. So they are, let's say they are building a SOC for a particular segment, then they don't want to build everything that is needed in the SOC. So people want to buy things that's not their core expertise, and then put a system together. Okay, so let's say somebody has cracked a great image processing algorithm, for example, right? So now to productize that image processing algorithm, the image processing algorithm is just one block, right? So now if you want to build a CPU around, like a SoC around that particular image processing algorithm hardware to sell it as an end product, then you need a CPU. Then like that particular image processing algorithm in a computer, like a compute system, has to, let's say, sit as a part of a card, and like a pluggable card. Then what I'm going to do is I have to like put some PCI Express link so that I can connect it to the CPU. So I will put a PCI Express link, I'll put my image processing algorithm. I might need a small CPU to manage local things, and then I need lot of local memory so that my image processing algorithm can work on that. So I'm going to put one DRAM controller. So now I have a SOC, I have a DRAM controller, I have my image processing algorithm, then I have one PCI Express core that allows me to connect to the CPU system, right? So now I need all these components. Now like if I have done an innovation on image processing algorithm, I can't go build all of these. So what I'm going to do, I'm going to buy these things, okay, and put my image processing algorithm over there, and then quickly productize this whole solution. And in order for that to happen, I should be able to easily buy off the shelf products and get going. Okay, so when you want to do that, the same concept even comes to the verification. So if I am buying an IP and I still want to build a system level verification environment to check whether my image processing is working properly or not, then I also need to buy various verification components, right? So how do you do that? So what you want is you want reusability of verification components either within a company from different project, or you want to buy it externally, right? And how do you do that? So for that to happen, we need the standardized framework for the coverage driven constraint random verification, right? So like for example, when I buy an off the shelf product, I know that my electric socket is compatible with the product that I'm buying. It's going to be that 230 volts and the 3-pin socket, so I can take it. So when I buy that, I know my home socket is going to support that because the whole thing has been standardized, right? So that is the benefit of standardization. So when you standardize something, the interoperability improves, and when that happens, we can reuse a lot of things. So UVM's main goal is standardize the framework for building such test benches so that you can buy or borrow components from different places, put them together, and since they understand how each of them are going to get connected and what is the overall big picture, I will be able to make it work. But if let's say in the absence, you might have seen within the system Verilog test bench, we didn't even have a standardized terminology to talk about, right? Like for example, we called the driver layer, maybe that is somewhat understandable, but when we said the middle layer as a transformation layer, that's a term that we invented. That's not a standard term. Now when we say that term, someone might think of it as something different. Okay, so how do we talk the same language? And not only that we communicate with the same language, also the components can be built such that they can plug in, and when somebody says some component name, we know what exactly it means, whether it belongs to the stimulus layer or whether it belongs to the second transformation or the functional layer or whether it belongs to the driver layer. I should be able to understand that, and then only I'll be able to buy that or borrow that and put it in my test bench. So that is the whole idea behind building the UVM. And so framework, that is one point, right? So that's the primary driving point because that's where the economics is involved, right? So ultimately somebody has to sell, somebody has to buy. If there is no economics, there is no real value for the technology. So the UVM's main the selling point is that different companies can build different products and they can sell it to each other, and then somebody can build a system together using those components and get some product out, right? Ultimately that is that commercial fact is what drives the technology. Now once that is out of the way, second comes the engineering, right? So in terms of engineering, what happens within the UVM is that we are able to like whatever the best known practices of how a particular good test benches needs to be built. We need to have the phasing, we need to have the flexibility in being able to override some things. So there are, and then how to separate out the different whatever the functionality to different modules, why it should be done that way. Some people have seen it over several years by doing several test benches. The different companies have seen the what works, what doesn't work. Now you need a way to deploy those best known practices. Just telling those is not sufficient. You want a way in which you can provide it in a form that definitely gets implemented. Okay, so that is where the this UVM framework, whatever the best known practices that are there in building the test benches, are all put in your base classes. So it's not just a theory. So I can say something and then I provide the base class and I ask you to implement it, right? So that is how the best known practices gets deployed and get implemented. Okay, and then it improves the consistency and portability because all the test benches, because of the way it is standardized, it's going to look very consistent. So now not only that I can borrow the components and build it, whatever I have built it at the IP level, I can give it to the subsystem level, then whatever the subsystem builds, it can be taken to the SOC level. So this way even there is a reuse vertical, right? And then as we have talked about, there can be even horizontal reuse. I have built some component for a particular IP. Let's say I have built it for UART. I can use the same thing for SPI. I can use the same thing for I2C. Whatever the APB verification component that I have built, I can use it across various peer products as well. So that is what is the benefit of the consistency and portability, and it's based on object oriented programming because we have seen like the concepts of abstract class, polymorphism, inheritance. Those are the the pillars that you require to build a reusable framework. Okay, so that's why it's built on object oriented programming, and without object orientation, if we had to build a methodology using the Verilog, it would not have been possible. I mean, I'm not saying it's not completely possible, it would not have become such a big success, because in order to have that success it needs to have flexibility to satisfy many applications, and if we had built it with a static Verilog type of a language, it would have become much more rigid. So and then it follows a transaction and transactor approach. We have seen this to some extent, like for example we had a FIFO transaction in which we package what needs to be done, okay, and then in the transactor we take that object and execute it and then do that particular operation. So you can also correlate this to an instruction and a processor, right? So what we are saying, in the instruction we are packaging what processor needs to do. I can say add two operands, multiply two operands, right? So in the instruction I am packaging it, okay. I'm not building like just the hardware and then I have to specifically give inputs and to use it. I'm not building that type of an hardware. I'm building an hardware where whatever I want my hardware to do, I'm able to package it in an instruction and send it to that guy, and that guy will execute it. This is the fundamental concept of building programmable thing. This is a basic programmability, right? From hard coded for example the hardware that was used in the calculator to the hardware that went into the building a general purpose computer, that was the main difference, right? So the chip that was built for the calculator specifically took inputs from your buttons, stored those and passed those numbers, very hard coded to that particular environment. But when you build a compute type of an environment, it works on the basis of instruction. So that is where the programmability aspect comes in, okay. So that is the same concept, you use it even for the building test benches, okay, and that is what is called as transaction and transactor. So transaction you can loosely correlate to an instruction, and transactor is the processor that processes that instruction and achieves the required intended functionality. And the way it gets deployed is deployed as a set of base class and utility classes. We will look at it, and the big benefit that you get is whenever you start building any test bench, you don't have to start it from scratch every time, right? There's already a framework, the skeleton is available, and you can use that skeleton and get started. So that is the benefit that the engineers gain. So this way, when both the engineering plus the business cost is combined, that leads to a successful product. So far we have not spelled out what is UVM. So UVM stands for Universal Verification Methodology, and what this means is it provides two things. It provides one class reference manual, okay, and then it provides an open source system Verilog class library implementation. So that's the second component it provides, and third, it provides user guide, okay. So when we say UVM, you get these three things, okay. You get a class reference manual and actual source code, so you can actually browse through the UVM source code. You should once in a while develop that habit of looking at the source codes, especially the library implementation, because they tend to use all the advanced features of the language, okay. I am not saying that you need to like master everything, unless if you are interested in eventually designing frameworks yourself, I mean you can do it by all means. But even if you intend to continue as a general user, it's once in a while good idea to expose ourselves to how the advanced features of language are utilized, because those are not something that we use every day. Like for example, the interface class concept of system Verilog, we are not going to use every day, right? But the UVM will make a good use of that. Polymorphism, of course we use it, but we may not hand design lot of polymorphic design in our everyday, but there is a fundamentally everything that happens within UVM, for each and everything it will rely on polymorphism, so it will give you that perspective. But remember that a UVM package, if you download it, you will be able to see these three things, okay. And it was initially started by an Accelera, and now it has become an IEEE standard. So the way this Accelera thing works is, it's a group of companies, so several companies come in and they will make sure that whatever is common, okay, which is not very key to their business but is still required, they come together, form a committee, and they will make that easy for everyone to do it, okay, so that the playing ground levels up. So then each company can go and do the primary innovation that particular company wants to do, right? Like similar to like the guy who is building an image processing algorithm doesn't care about what innovation is required in PCI Express or how the processor needs to. He just wants some ecosystem in which his stuff can sit in and he can deploy, right? So now what these companies will do is they'll come up, and then whatever is a common problem they will say we'll solve it together, and then whatever, they will have their own secret sauces that they will keep it and they will build further on the top of that, right? So Accelera is one such group of companies wherein these people collaborate. Even when you join companies, you can become a part of the the Accelera, so you can register yourself through your company. You can participate in defining new things, so that's a good area for you guys to explore eventually. And IEEE standardization gives much more strength, much more formalness to the whole the effort that has gone in. Okay, so that is the main thing. So even both the system Verilog and UVM now have become IEEE standard. Okay, so let's quickly look at what is the definition of methodology. A methodology is a system of broad principles or rules from which specific methods or procedures may be derived to interpret or solve different problems within the scope of particular discipline. Okay, unlike an algorithm, a methodology is not a formula but a set of practices. Okay, so this is what it is. And I know this might sound very technical, but in layman terms, what I want to translate this statement is, so think of UVM based classes as set of application forms. Okay, so you might have seen application forms, right? You might have filled it up for like taking admission to a college, or maybe getting some government IDs done. You have filled a lot of application forms. So what does those application forms contain? Whatever is fixed. For example, I'll have name colon, address colon, mobile number, right? Maybe my Aadhaar card number. So on and so forth. I will have different fixed fields which I need to fill in. Okay, but those fields which are fixed, the order in which that information needs to be provided is all fixed. Okay, so now with this, what happens? I can't just write whatever I want, right? Like compare that with if somebody gives you a blank paper and say, give me your information. Then you don't know whether do you need to provide PAN number and Aadhaar number, or do you need to provide only one of them. You don't know anything about that, right? So when I structure it, then okay, these are all the set of information that I'm expected to provide, right? That's the structure that an application form provides, and different people can take that application form and fill their information as to what they want to, whatever is specific to them, whatever the options they want to select, they can fill it and give it. Correct? So that is the power of the building application forms. Now what UVM does is, each of these UVM based classes you can loosely correlate to an application form. Okay, and the fields, that fixed fields that I'm talking about, those are nothing but your tasks, functions, various macros that we will see that are defined within the UVM based classes. Okay, now that is why every time when you see the inheritance, when we see the use of polymorphism, what happens is those are placeholder functions. Okay, that is how you should implement. Like when I say name colon, the actual name is not filled, right? So the function that I have defined virtual is just a placeholder function. Internally it doesn't have any functionality, but it is saying you have to implement certain set of functionality through this set of functions so that it is standardized. Okay, and we can all speak the same language. That is why it is standardized. Now the benefit of that standardization is that now this function is fixed. Somebody can call this function, right? Without knowing how it's going to be implemented, somebody can call and do something more with that particular function. And then as a implementer, what I'm going to do, I'm going to derive this particular class, which is like an application form for me, and I'll fill in my information in each of those tasks and functions. And if I fill it in, further processing will take place, because that form somebody will take and put it in a system, and then it moves through. You are not moving your information through the system. Like for example, when you are opening a bank account, you just fill the application and give it to your clerk, right? And he will put it in a system, goes through set of verification, everything, and eventually you will get your passbook and checkbook, right? And your various cards. Same thing will happen over here. There is a lot of processing that is done internally within the UVM, which you don't have to worry about it. As long as you fill some of the information that is required to implement your verification requirements, the UVM will take care and do the rest of whatever is the common thing that is needed. It will do it on the behalf of you. You don't have to worry about it. But in order to use that common thing, you have to implement your stuff in the form that is specified by the UVM. So that is the main core idea. Okay, so you can actually download the UVM implementation. So the current one as of this 2023, we have the latest version as UVM 1.2. So I have downloaded this package, and once you download this package, you and sort of unzip it, you will be able to see these various documentation and the source code available within that particular directory where it is unzipped. So you will be able to see this UVM reference manual HTML, and within this, that's the class reference manual that we talked about, and within this docs folder you will be able to find the user guide that I talked about. Okay, and then within this source folder, okay, you will find all your classes. Okay, so now if I go and into this particular say, and I'm listing everything in the source folder, you will be able to see that I have the various base classes, components, and then macros, sequences, TLMs. These are the things you will be seeing shortly. So we will figure out what are the different base classes which are equivalent to application forms that are available, and how to fill them. That is all that we are really going to learn as a part of UVM. What are the different application forms are available, in which conditions do I need to fill those forms? If I want to do a fixed deposit, which form do I need to fill? If I want to put some money into my account, which form do I have to fill? So think of it like that. For everything there will be set of forms, you fill it, and when you fill it, that particular operation will take place. And along with that, there will be these two key files, the UVM macros.svh and UVM package.sv. So if you remember, whenever before any UVM usage, we are going to import this package. So you'll say import UVM package scope resolution operator star. Everything from this package will be included, and we will do tick include of UVM macros.svh. So those are the two things that we do, and those real files are present. So you can anytime, you don't have to feel that everything is hidden from you. You can go there and actually look at them and understand like how things are happening. You don't have to go very deep into each one of them to understand. Just have a look at it, and it will give you it will give you a sort of control that yeah, what I am using, I can really see it. Okay, so this is the screenshot of the class reference manual. So what you need to do is just need to open that particular HTML file that's provided. So once you open the HTML file, it will open up like this, and on the left side you will see the the sort of table of content. In a way, it's a table of content, and then you will be able to see different classes. You can click on each one of those classes and look at it. They are well categorized and organized. So each one of them, you can click on each of those sections. I want to look at sequencers, I want to look at TLM, I want to understand components. So each of them you can click. So what happens is, when you write the classes, the system Verilog classes, there are tools, like one of the tool is called Oxygen, wherein whatever the comments that you put in your source code, what those tools will do is they will go through those comments. Like you have to put a class header where you specify what this overall class does, and then for every of your public function that you intend to expose to some usage, on the top of that you are supposed to put like a comment saying what that particular task or function will do. So that's the right way to write the code, which becomes maintainable. And these tools are capable of going through your source code, extracting your class hierarchy and extracting whatever the comments that you have put, and they'll organize it. So now what happens, I go to a particular class hierarchy, I click on that, then I will be able to see all the, like whatever the description that I have put in my source code. Okay, and that becomes easy for me to understand. It will all show the, like for example, show the function prototype, and it will show me the description. So that way, it becomes easy for me to understand how the code has been structured, because ultimately I'm extending that particular class and I'm using it, right? So if I have to extend it and use it, then I need to know what are the public properties that are available, what are the public functions and tasks that are available, how they are, what is their prototype, because ultimately I am supposed to implement it. So whenever I need to do that, I can come to the class reference manual, go to that particular class and understand like what does it contain, so that I can go ahead and implement it. Okay, so you guys should all open and look at this particular document, and keep looking at it once in a while, so that you get the familiarity of how, because the language used in different guides is different. Okay, the class reference manual will speak a different language, UVM user guide will speak a different language, system Verilog LRM will speak a different language. and it is important that we get acquainted with it so that when need comes, we can look at that particular language and understand it. Although it's English, the different these guides use a different form of English. Like what does it, like if it says should, what does that mean, right? So there are technicalities like that. So when you read through it, you will be able to understand. Okay, so UVM has come a long way, and let's quickly look at how it has evolved. So the early stage, I think like we had the Synopsys developing a Vera language, and based on that Vera, which is also was a high level verification language, based on that they had created this methodology called reuse verification methodology, which was called as RVM. And then Cadence was developing their own, I think it was some different company, so which got acquired by Cadence. So they had this language called E. It's being used today. It has lost the popularity, but those who use it, who have used it, find it very very powerful. So the Specman E, and then based on that Specman E, they had created this E reuse methodology, ERM. Okay, so that still continues to exist independently. It's a different language altogether, but anyway the concepts sort of bias each other, so that's why I'm bringing that up. And then of course the system Verilog got introduced, and then different companies were building different methodologies. So there was a VMM which was promoted by Synopsys, which is called verification methodology manual, and then there was an advanced verification methodology that was another EDA company. I forget the name that they were creating it. And then there was one universal reuse methodology. So we have basically three major EDA players, and each one of them were sort of doing their own verification methodologies. And then at one point of time, this advanced verification methodology and then this universal reuse methodology got merged, and they created this open verification methodology. And then open verification methodology kind of merged with the VMM, and then they came up with VMM 1.2. And eventually from VMM 1.2, I think all three companies collaborated and defined this universal verification methodology, UVM. So this is a the amalgam of multiple verification methodologies and practices. And the reason, as I told at the beginning of the session, that I am bringing this up is that you will see that the UVM is big, and then there are some to do same thing, there are multiple ways that are available. That has happened because it has merged from so many different verification methodologies, right? And then every one of these had their own philosophies. And so although unique things have been taken, but there are cases where some of it is still redundant. So that is why it has become bloated, and there is some redundancy which we need to navigate. Okay, this is the overall scope of what we are going to learn in UVM, categorized into few categories so that it's easy for us to remember. So the top level is where we generate various stimulus. So sequence item, you can think of it like equivalent to our FIFO transaction. Sequence is equivalent to where we were putting a loop and generating series of random push and pops. Then there's a concept of virtual sequences. So what happens is that if you want to run sequences on multiple physical interfaces at the same time, then you use the virtual sequences. That's like, think of it like if I want to run push and pop together, right? So then you use the virtual sequences, which will create the parallel traffic. And then the second level is all your test bench components. So agents are something where it consists of like a sequencer, on which, like, sequencer is kind of in a way equivalent to your generator on which you run these sequences. So that sequencer will now generate a series of sequence items, and those will be sent to like a driver. So agent will also contain a driver, and it will drive the interface, and it will also contain a monitor. So an agent is a combination of sequencer, driver, and a monitor. We'll see in more detail, just giving you a flavor of it. Then you can build independent components if you want to build an independent checker, or even if you want to build some sort of a transformation logic, you can put all of that in the components. Then there's a concept of subscribers, which we will see. These are used for building your coverage monitors, right? So if you want to build a coverage model, you typically build it in the subscribers. So the name subscribe is indicative of that it subscribes to various transactions from different components and consumes it to produce functional coverage. Okay, can be used for doing something else also, but the basic idea is that it can subscribe to different test bench components and take those transactions and do something with it. Then you have these scoreboards. There are some base classes that can help you ease the process of building scoreboards. And then we have environment class, like if you remember, we had doing a lot of like sort of build, connect, and then run, finish. So we had those set of series of tasks that we had defined within the environment. So same thing, this will standardize and provide it further. So there's an environment based class for that. And then end you have the tests. So the basic idea is the environment will instance all these guys. So it will instance agents, components, subscribers, scoreboards, and then tests will instance environments, configure them, and run some series of sequences on the agents present within the environment. That's the basic idea. Okay, and then there is a third layer wherein all the test bench components that we have created, agents, components, subscribers, scoreboards, all of them now need to interact with each other, right? So there is something called transaction level modeling. These provides the ways for these components to communicate with each other. So like we had the mailbox, so in a way it's sort of advanced mailbox type of a concept using the TLM is implemented. And then if you have some classes or interfaces that we need to pass around, we were passing it through the constructor, but that sort of ties it down, right? So now whenever we instance, we need to pass it, so the flexibility reduces. So then there are set of these databases which are global in nature, through which you can put something in the database and some other component can take something out of that particular database, right? So there are these config and resource DBs. There's a concept of factory. If you remember, in our FIFO test bench, we are overriding the config to create a different set of transactions. So in the UVM, that concept is standardized with the help of factory. So you can override a particular object using factory. As a concept of objection, wherein test can say that, okay, when the test should end, right? So when the test should end is controlled by an objection mechanism. And then there is a phasing, right? So phasing is, as we talked about, like you can do when the test bench component needs to be built, when it needs to be connected, when do we run the test, and how do we end the test, how do we report it, all that are defined as different set of phases. So then there's a phasing concept. There's the third thing that kind of glues all of these components that we have defined as a test bench environment. Apart from that, there is a lot of utility classes that these guys can use. There's a reporting utility classes which is made up of set of macros. So let's say you want to log some messages within the test bench, then you can log it with a different level of verbosity control. Some messages that should appear all the time, some messages that should appear only when I enable certain type of options. Like that you can configure using reporting. And then there is a concept called RAL wherein whatever the registers that are contained within the design, you can model them using the RAL. There are more utility classes, but these are the core utility classes, and this is the core set of base classes that you can utilize to build the test bench. In summary, you have a sequences, different types, which is your primary stimulus generation mechanisms. Then you have agents, components, subscribers, scoreboards, which are the primary thing that will implement all the functionalities of your generator. Then the middle functional or transformation layer, drivers, the three layers that we had talked about in the system Verilog test bench architecture, those all will be done by these guys. Okay, and then all these guys are instanced within the environment, and then the environment is instanced within the test. And then you have this bunch of gluing options. Through the TLM, you connect these components, and through the config and resource DBs, they can exchange some other information, which is like if you are generating transactions, you want to exchange it through TLM. But if you have some object that you want to exchange, like for example, we used to pass FIFO config to all the other components, that you can pass it through these DBs. Okay, and then you have factory for doing the override. Override is what allows the test to override various things so that it can configure the environment in a way that it wants. Objection is a mechanism that you control the end of test, and phasing makes sure that you are ordering everything in a way that the test execution is well defined. You have utility classes, reporting, and RAL, which help you do it more efficiently. So this is the broad lay of land for the UVM. Let's correlate the groups that we saw in the previous slide to the actual base class hierarchy that we have in the UVM. So there are about four, like we had seen those four categories of items. So how those 4 categories of items are organized in UVM base class hierarchy, let's look at it. So when I mean base class hierarchy, what it is, so you really, there are classes, and some class, when it says extends this particular class, then it becomes a hierarchy. For example, I have a UVM object, then a UVM report object will extend UVM object, so it becomes hierarchy. Now UVM component will extend UVM report object. So this is how the hierarchies are built, and these hierarchies are built because we want to inherit some common functionality and build on the top of it to satisfy certain category of requirements, right? So that is the whole idea. That's what is called as the class hierarchy. So we have the UVM object at its root level, and then don't take it for a UVM root component, but for this particular discussion there's a separate something called UVM root. We'll come to it, don't get confused with that. But UVM object is the main class from where all the deriving process starts. So from UVM object we extend and create a UVM sequence item, okay, and from UVM sequence item we create UVM sequences, okay, and then we also create this UVM TLM generic payload. Don't worry about it, but look at it this way. So you have UVM object, UVM sequence item, and UVM sequence. So this is your stimulus generation related base classes, okay. So whenever you have something to do with the stimulus generation, you will extend these guys, okay. So you see here there is this method called body, right? So this is where you actually implement the stimulus generation. So I had talked about it, that these are the application forms. So if you look at it, this is a UVM sequence application form. Main thing that I need to fill in is the body, okay. If I fill in the body, it will generate the stimulus. So that is the very basic idea. Then you have UVM object, and then we are extending to UVM report object, and then we have UVM component, okay. So this UVM component is now base for rest all the other components that we are talking. You can use UVM component independently. If you remember in our second box that I had shown in the previous slide, it was related to the components, right? And then along with the component you had the agent, right? So and then you have the UVM driver, you had UVM sequencer on which you can run the UVM sequences. You have a UVM monitor which will monitor the interface and generate transactions for you, and then we have UVM scoreboard base class where you can implement all your comparison functionality, and then you have UVM env which is your environment, okay. So and then this UVM component is also extended to create the UVM test, and in the test we'll instance this environment and run these sequences that we have defined. That is the basic concept, okay. And then if you look at it, everything is an application form. So if I look at UVM component, I have these phases. So I have this build phase, run phase, right, final phase. I'm not showing all of them over here, but these are the various phases. In those phases I will implement functionality, right? For example, you remember we had created run task in each of our system Verilog components that we had used in the FIFO test bench, right? So the same concept, right? So now instead of calling our own name run, now this run phase name is standardized. So anything that core functionality that a component needs to run, you can put it in the run phase. And the good thing is the UVM itself will create a thread for you. You don't have to even fork off the threads, right? We were forking off threads in the FIFO test bench. You don't have to do that. So UVM itself will do it. And when a UVM driver extends it, it will also get all these methods. So UVM driver will also have a run phase. So all these this particular hierarchy, that is a hierarchy of components, and these components like driver, sequencer, all of these are components and they are active components. They will have a thread and they remain throughout the duration of simulation. Whereas this sequence item and sequences, they come and go. There are lots of sequence items that get created. Like we had FIFO transaction, many of them were created. Same way a FIFO transaction in a UVM would be modeled with a sequence item. So a lot of them will get created, okay. And then sequence, you run one sequence, after that run another sequence. But the components like driver and then your generators in the form of a sequencer and then your environment, they will remain forever, right? Forever means from the beginning of your test start to the total test end, these components will all remain. Now if you look at the third hierarchy that we were talking about, the one that helps you pass objects around, this was your UVM resource. You have a UVM resource DB, and then we have UVM config DB, in which you can put the objects, and then you can help these components share that particular information among each other, okay. And then you have the fourth layer, which is our utility classes. So you have this report catcher with the help of which you can configure your report generation logic, and then we have that UVM RAL layer that we had talked about. So you have UVM reg, which helps you model each of the register in the DUT. You have reg block, reg file, reg field, then UVM mem. So all these help you model your RAL functionality. So these are all utility classes. So this way how the broadly the base class hierarchy has been organized to satisfy different requirements. Okay, so this is how the overall UVM test bench looks like. So you'll have a design under test, and then you have this UVM test, and then what happens is the UVM test will instance the UVM environment, and then this design is connected to this UVM environment using the set of system verilog interfaces, and those interfaces are passed to the environment using the config db, and then from one, so and that at the top level UVM test bench will connect the system verilog interfaces to the design and then put it them in the config db, and once we put it in the config db is like a global object, and from that object each of the agents will extract that particular interface. Inside the agents it will have driver, monitor and a sequencer, and then the test will instance this particular environment, and as we talked about, the test will have access to various of the sequences, configuration and the factory based overrides. So the factory based overrides helps if they want to change this particular environment, it can be changed using the factory overrides, and then using that it configures this environment that is instanced to create the configuration that it wants to test, right? So the tests will always randomize two things. They will randomize the configuration that they want to test and then generate the stimulus that matches the configuration that they have selected. Okay, and note that the UVM environment can be containing other UVM environments as well. So like for example, if you are building like a IP level environment, you may have a single environment, right? Let's say. Now what can happen is that at the IP level I have done it and I take it at the subsystem level. Now I want to bring in that particular subsystem is now again a group of IPs, right? So now I want to bring one of the lower level IP environments into my subsystem level environment. Then what I can do is the IP level UVM environment, I can just instance it as is at the cluster level, right, where I am testing the group of IPs, right? So for each of the low level IPs, their whole environment I can just bring it in. Okay, and then through configurations and the factory overrides, I can then later decide whether I want to keep that environment active, not active, or I want to change certain things about it. I can do all those from the test. Okay, the test has the full control because test instances environment, and through configurations and factory mechanisms it can change the way environment has been created, right? So when I code it, the environment will be in certain way, but from the test using this factory and configuration mechanisms, I can change how the test bench is structured to suit whatever the configuration that the test wants to test. Okay, so once it has configured, it will take the sequences and it will run it on the sequencers, and those sequencers will run and create a series of sequence items, and then that will send to the drivers that are present within the agent, and then the agent will drive it out. It will also have the monitor, and those monitors will monitor the interfaces and pass those to the scoreboards and the coverage monitors. Coverage monitors will cover it, and then the scoreboards will store the stimulus that is generated as well as the responses that are seen, match them up and tell you whether it is passing or failing. How long the test should run is controlled by the objection mechanism. I know these all terms may not be very clear. Don't worry if it is not completely clear. I'm just seeding those thoughts and ideas at a higher level. We'll go deeper into each one of these ideas and understand how exactly they work, but I just wanted you to understand a big picture here. So the entire, like what I showed you in the previous slide, the class hierarchy, that's only like is a subset of class hierarchy that I showed you. There are a lot of UVM base classes, and as you can see, I'm just showing a mind map of how the different classes are organized and what is the hierarchy. So there is a mind map available that has been extracted. We have extracted that, so I will send you that mind map, and then you can explore the different class hierarchies. So I've taken these numbers from this particular paper. So you can look at this paper. This is a very interesting and useful paper. So we are going to be using some of the concepts from this paper as well to implement to structure our learnings as well. So if you see the base classes, we have about 357 base classes, method definitions within them 938. The methods that the users can call are up to 99, and then macros we have about 374 macros. These are the shortcut macros, like you can for reporting, let's say I can say tick UVM warning, tick UVM error, so something like that. There are a bunch of like tick UVM do for running sequences. So there are several macros that are available. They act as a shortcut macros as well in some cases. So there are 374 overall. If you look at it, this is a big size, right? Now the question will come in your mind that why is it so large, right? And to some extent we have been saying, we are pointing, so this is also that universal, meaning that it targets all flavors of designs possible. So there are capabilities that are present in the test bench that might be useful for one category. Like let's say you are doing a processor design verification, there will be some capabilities that you would be using. If you are doing protocol verification, you would be using a different set of capabilities. So and if you are using some sort of an encoding decoding mechanisms for error correction, then you will be using it in a different ways. So for satisfying all flavors of design, the different set of categories that have been put in place. Okay. So that is why what has happened is the size has become very big. Okay. And the other point that we have been pointing and we have been looking at it, the UVM was not a clean slate. That is, it's not that somebody decided we'll build the UVM and it was created, right? It has evolved from VMM, OVM, and then having to sort of showcase that unity in diversity, right? So it's the amalgam of so many things. So that because of that, it has become bloated, and then there are some redundant set of classes, methods, and macros. Then mainly like mostly some of them are like same with very slight or very obscure meaning like very fine differences that doesn't much matter to the day-to-day work that we do. So there are many methods and macros that do the same thing or nearly the same thing. That's because there are two things that have come from the methodology, right? And two different methodologies, when they come together, there'll always be some things that are common, correct? So that's the idea. Like for example, if two set of people are staying at two different places, when they come together and plan to stay in the same place, then you can just imagine, right? Like probably there will be two refrigerators and in a same house. So it's the same problem with the UVM as well. So we have field macros versus functions. So same thing, you can do it using the functions as well as using the field macros. So sometimes that can be confusing as well. And then among class hierarchy, it's not clear like which is meant for internal use and which are for end user. Like when we say 357, not all 357 are really useful for the building the test benches, right? So some of them are only meant for internal usage, right? So there's not something that directly user extends and uses it. Okay. So but what happens is it's not very clear as to which one is for the user and which one is not. Okay. And because of that, it appears very large and at times confusing. So unless we have a right strategy to deal with it, it can be hard to master the UVM, and we can very easily get lost. So good news is that we have a strategy, right? So our strategy is going to be, we are going to be focusing on these three things. So first we will look at some of the core concepts that won't change, right? So think about it like this, right? So UVM is a methodology, and UVM can be implemented in some other language as well. It's like today it has been implemented in System Verilog. It doesn't mean it has to remain with System Verilog only. There's already a PyUVM that is coming up, which where the UVM is being implemented in Python. Okay, similar to that, similar to you. So what UVM represents is it's an application form. Right now, I can print different formats of the application form. Right, it doesn't matter. So so it's the concept of how something needs to be done. Now that can be implemented using System Verilog, that can be implemented using Python. Any language that provides the object orientation can potentially be target to implement a methodology like UVM. So what we are going to focus is one aspect is that we will focus on concepts that are not going to change, so that even if tomorrow something new language comes in, at least this base investment that you are doing gets protected. And second thing, we will focus on like a common subset of base classes that are used in most projects, right? Like we'll not worry about all the classes, all forms of applications. No, we'll focus on common subset of base classes that are definitely going to be used in most of the project, so that within the short span we learn most of the useful things about UVM. We cannot learn everything about UVM. It's very hard, right? Even if you spend 10 years, you might still not use one of the base class, right? So that is something that cannot be that cannot be guaranteed. But what we will do, we'll focus on the common subset that is most useful, most likely going to be used in every project, right? So we'll focus on that. And third thing is, we'll focus on one working example, the UR test bench, so that you get that pattern in your mind, so that at least one pattern is very clear with respect to UVM usage. So these are some of the concepts that are used by the UVM. So it's delivered as a system Verilog package, and during our system Verilog package session also we have discussed as to why it's delivered as a package, because it's pre-compiled, so it's able to load very quickly. And then there are we had seen during the compiler directives, you can use macros with arguments, that sort of acts as a way to generate some code. So that is what is used by UVM as well. And it has used parameterized classes heavily. So all the base classes that you use, they will be parameterized. And then the data type based parameterization, that is something that you're going to see very much. There is a polymorphism that is used. Along with that, also the concepts of interface classes are being used within the UVM. There is a good bit of usage of scope resolution operator, you will see with some of the base classes. And then there's a concept of abstract classes and static methods. This also is heavily used in UVM. So some of these you will be able to experience it, right? But internally it uses DPI as well. That something may not be visible to you, but yeah, it internally even uses DPI. So along with all the basic concepts, I'm just telling you some of the advanced concepts that the UVM is using. I mean, of course, it's using the classes, using various data types. That way, it's using almost all the capabilities. But these are some of the advanced capabilities of the system Verilog that UVM has utilized. These are some of the core concepts of UVM that we will be looking at in the coming sessions. So how do you separate test intent from environment? So if you remember the UVM test bench diagram, the test was instancing the environment. So and then it was separately running the sequences, right? So if you remember that block diagram, then what that means is whatever test wants to accomplish is separated out from what the environment does. So that way, sort of environments remains a separate thing. Okay, like again going back to our analogy of like an instruction versus processor, right? So test is creating series of instructions, and environment is acting like a programmable processing engine that can process whatever the test wants and execute it. So when those two are separated out, what happens is that you can build much more generic environment, and then test can use the specific capabilities on the need basis. And then there's this component versus object concept that we have seen. Components are also class based objects, and this object is also object, but sort of the terms are little overloaded, but objects are essentially a transaction if you want to rephrase it. So components live through the entire duration of the test, whereas objects, multiple of them gets created and destroyed. Then phase is a very important concept. So we look at like how the test bench is built, how it is connected, and then how do you run it, and then how do you clean up the test environment after running a test, and how do you report it. So we look at it in the so these are all standardized now. So we look at the phases. Then TLM is a concept for communication. We had used mailboxes, whereas UVM provides like a transaction level modeling based communication mechanisms. Very useful, not only useful in UVM, but even if some of you do the system C based modeling, there also TLM concept is useful. In fact, the TLM itself in the UVM is borrowed from system C. So as we have been seeing, UVM has borrowed from multiple places. From the various methodologies it has borrowed from the system C. So TLM is defined in system C, and again there it was implemented in system C language, but now here it's re-implemented using the system Verilog. Then we have concept of sequencer and sequencer, where again as the same idea, you create a series of sequence items and the sequencer will execute them and interact with the driver to send it over there. As an interesting concept of factory, so using the factory you can override certain classes within the environment to reconfigure it to meet the test intent. Then there's the end of test. So when after generating the stimulus, how do you know that every generator is done, and even your scoreboard thinks that it has matched everything, and it's now we can end the test? How do you decide that? So there is a mechanism for that. And then there are a set of macros, like how do you use those macros, right? So that is the another core concept that you need to look at. So again, these numbers that I have derived it based on this paper. And what we are going to do is we are going to study much broader, slightly broader than what we are saying over here. But what you need to keep in mind is that these are the core things that you need to like pay attention and build some depth, because these are the common base classes, or about 11 common base classes that are almost used in any UVM based project that we will pay more attention to. Then common methods are about 9 methods that you need to absolutely. So these are the things where you need to sort of know these things well, and you should be able to answer if there is any questions. So those are these areas. So there are about 21 method calls that you should be able to know them and be able to tell how do they work, and there are about 7 macros. So this is not a very huge number. But however, I am telling you that we are not going to restrict only to these. It's going to be slightly broader than this, but this sort of identifies the target areas where you need to have certain level of depth. Okay, so what are those, right? So the base classes that we want to make sure that you are very clearly understanding them are UVM test, UVM environment, agent, sequencer, driver, monitor, subscriber, right? So these are all, if you remember from the class hierarchy, these are all based on the UVM component hierarchy, which is an active component, meaning they will have some sort of a threads internally and they will live throughout the duration of test. And then there are certain object based classes like sequence for constructing stimulus generation, sequence item for modeling transaction. Then there's a concept of analysis port, which is used for distributing the transactions from monitor to different like a scoreboard, coverage monitor. So one to many type of connections can be done using the analysis port. It's a form of TLM. And then we have something called analysis imp export. So when we studied the TLM, you will be able to understand these two. So these are ways to connect the components. Okay, it's a very important TLM port. And then bunch of methods that are important, new, of course you guys are already aware, constructor. Then the set of phases, you have build phase, connect phase, report phase, right? Build phase is where we construct all components, we connect them through the TLM ports. And then report phase is where we report how, like what the test has done. And then run phase is where we run all the concurrent threads where actual time gets consumed. And then there is a task body which belongs to sequence, where we create actual stimulus. Whatever we create in the body of the stimulus gets processed in the run phase of these components. And then we have this write method which is used with the analysis port. So when you write it to that particular analysis port, it gets broadcasted to all the connected components. Don't worry too much about it, we will look at it. And then we have phase ready to end, the function which tells when any of, like you can pass a phase and make it wait for certain that particular phase to end from all the components point of view. See, all these components will have all these phases. Okay, so if I want to wait for a particular phase to end so that I can do something, I can use this particular function. Then there's a response handler. So what happens in the sequence, if I issue a transaction type for which I need a response, like for example I issue a read, now I need to get back the read data, so I can use the response handler concept. This is also one of the concepts. There are multiple ways to extract response, but the response handler is one such concept, so we'll look at it. Okay, so the other method calls which we will be using, so the sequence item port, this is again another TLM type of a communication mechanism, very loosely connected to mailbox in terms of intent, not in terms of implementation, but in terms of intent. So get next item will help you get, like, it's kind of equivalent to the peak that we had implemented in the loosely equivalent to the peak that we had implemented with the mailbox. Then item done to tell the sequence that okay, this particular transaction that you had sent is processed. Then we have standard get put type of methods which we have even seen in the context of mailbox. Then the analysis port dot write which you call to write the transaction to port such that it can be broadcasted to everyone. Then we have sequence start and finish. Within the sequence you will start item and finish item, which then will initiate communication with the driver. And then we have bunch of macros. We have object utils, component utils. These are called factory macros. We will look at it in the detail. And then we have bunch of reporting macros for for indicating a fatal error, warning, info, different type of the verbosity control, the level control you can use depending on the type of information that you want to display in the UVM info. So we will see all these aspects in detail when we go to the subsequent slides. And then you have this UVM analysis imp declaration. Don't worry about it too much. It helps us create multiple analysis ports within a component. So how it helps, we'll look at it. I know this is a very quick flash through of the information, just to make sure that you get to know few terms which are important. You might want to make a note of these things so that when we talk about in detail in different contexts of core concepts or implementation, when these concepts comes, you want to pay attention to make sure that these basic concepts you have achieved higher level of clarity. So this concludes this session on introduction to UVM, and we know now what's like the business intent of UVM, the reusability, so that the multiple vendors can share and sell components to each other, and then the engineering aspect of it, that we want to make sure that all the best known practices are available to engineers, and then every time we start building coverage driven constrained random verification, we don't need to start from scratch. We have a bunch of these base class libraries, and we build it in a standardized format so that even when some person moves from one company to another company, he doesn't have to think, oh, what is this? There's some terms that are invented and you need to sit learn the same things called in a different way, right? That type of problem will not be there. So whole process is standardized. Everybody, when they say UVM agent, it means the same thing. So that that type of the consistency the UVM will be able to provide. And UVM is delivered in the form of three things. You have the class reference manual, you have the set of base class source code, and then you have the user guide, right? So these three documents are get delivered. It's available, you can download and look at each one of them. And then before any UVM usage, you import the UVM package. You say import UVM package star, and then include the UVM macros, right? So these two statements you do, and then entire UVM becomes available for your usage. And then we quickly looked at the class hierarchies. Class hierarchy means how one class has extended another class to build this whole base class library. So we saw that we had those four categories. First category for the sequence, category of sequences which are used for the stimulus generation. The second category of components which are primarily used for implementing your driver layer, functional layer, and as well as your stimulus generators, right? So it's used for implementing all your test bench components, and they remain throughout the duration of test, whereas the sequences and sequence item, they come, they get created and they get destroyed. Then the third layer, where it provides the way to glue all of them these together, the TLMs, then the configuration databases, factories to help configure it, and a bunch of utility classes for your reporting information from your test benches into the simulation log, and as well as for doing the RAL implementation, which are some of the key utility classes, and we saw the evolution of the UVM, and we also saw that because of that it has ended up with more than 300 plus base classes. And learning UVM is, we saw that it's a way we learn some core concepts and then we have to learn all these base classes. And we also saw that not all of them are equally important. Because of the evolution, there is some level of redundancy that we would be seeing, and we discussed about our strategy to go crack the UVM. So our strategy is threefolded. First cut, we will understand all the core concepts that remain same irrespective of whether today UVM is in system or tomorrow you go to PyUVM, any of those areas. So those core concepts will always remain same. So we'll make sure that you get a good grip on those core concepts. And second thing, there are multiple, because it's universal, so it is capable of supporting different types of designs, and hence certain classes tend to get used in only certain types of designs. But what we are going to focus on is the common subset that's going to be useful in every environment. So we have identified those subset. I have shown you a few of the key terms that you might want to make a note or at least take a screenshot and save it, so that you can, when we discuss further, you can relate to those and make sure that you build some level of depth within those concepts. So in the upcoming sessions, what we will do is we'll go through the core concepts. We'll go through those some of the key base classes, methods, and then their calls and the macros. So we'll go through those in detail, and then we will conclude it with the help of a real test bench example to make sure that you get a good grip on UVM. So yeah, thank you for listening.